All right, well, good morning. Welcome to the emergency COVID version of Zoom for Mat106. Yeah, I came down with COVID this weekend, so hey, I'm not going to be on campus. So anyway, but we're going to do basically what we normally have been doing in class, just on Zoom. So I'm going to start off like always and just say, hey, is there any homework that we want to look at? How's that stuff going, by the way?
It's not too bad. I think there's one that I couldn't get, but other than that, it was pretty easy.
All right, do you want to look at that one, Nick? Which one was it? While he's
Sorry, I
looking.
kind of lost the screen for a sec.
Oh, no, you're all good.
It's number 8, I think.
Okay, well, let me go take a look at that, and yeah, we'll
It
take a
was
peek.
like it was just one of the ones that had the natural log in it.
Okay, and I just want to make sure this is exercises 2.3, the volumes of revolution.
Yeah, 2.3.
Okay.
Yeah, it was number 8 that has the natural log.
Okay, well then let me go ahead and switch to that. We'll take a look at it real quick. All right, so here's number 8. And it says we want to use cylindrical shells to find the volume of the solid generated by rotating the curve y equals 3 natural log of x about the x-axis for x's between 1 and e. Okay, so this one, it says use cylindrical shells, but we'll see if that actually makes sense for us here or not. But real quick before I move on, I see Douglas just popped in. Hi, Douglas. Welcome to class. Glad you were making it.
Hello, I'm gonna have to go around 8:50 to go drive my mom to work, but I'll be back.
Okay, no worries. I am recording this and I'll have it, I'll put a link to that in the Canvas shell when it's done. So you can go back and see what you missed.
All right.
All right, so let's take a look at this problem. So we've got y equals 3 natural log of x, and we're going from 1 to e. All right, so before I go too much further, everybody sees the whiteboard? Yeah, no, thumbs up?
Yes.
Yeah, I can see it.
Okay, cool, thank you. All right,
Yeah,
so I'm gonna start just on the graph of this thing. So 3 natural logs of x is gonna look something like this. All right, more or less. That's a natural log. The 3 stretches it by a factor of 3. And since I didn't actually put any units on here, we can call that good, right? So we got y equals 3 natural log of x. And we're between 1 and e. So x equals 1 is going to be the intercept right here. Because when you put 1 into a natural log, you get out 0. And then if we plug e in, the natural log of e is 1, and 1 times 3 is 3. So somewhere out here is x equals 3, or sorry, x equals e, which is y equals 3. And so we're looking at this region right there, that kind of like curvy region. All right, so there's our picture. And then we want to rotate this about the x-axis. All right, so we're going to go around the x-axis. Oops, sorry, hit the wrong button. So we're rotating this way. All right, so there's our picture. Now, it did say, let's use cylindrical shells. Now, if we didn't use cylindrical shells, this one would be pretty easy with discs, at least in terms of the setup. Because you can imagine if we take that shape and go around, We're going to see that kind of thing. So if it was going to be using the slicing method, we'd have disks that look like this. And so we would just have to do the pi r squared, and we'd be good to go, right? And in fact, let me go ahead and set that up, and we'll talk about why we don't want to do this one this way. So our volume then would be the integral from 1 to e. We're going in this direction. We need our cross-sectional area, which are circles. So it'd be pi r squared, and the r is determined by the y coordinate of the point. So it'd be pi y squared, and then times a little dx. Now, of course, we've got both letters, so we'd have to replace, but we've got what y equals. And so if we were to do it by slicing, it would look like this. And I'm going to just pull out the 9 pi. The 9 came from squaring the 3. Just so you can see what we're integrating here. All right, so this would be the approach by slices. Why might that not be what we want to do? Can you see potential issue with that? How about I'll give you the issue. What's the integral of natural log squared? And you should all be shrugging your shoulders and going, oh.
Yeah, I don't know.
Right, because we have no way of doing that. Our only attempt would be if we were to let u equal natural log, because then you go, okay, cool, that's u squared. But the problem is the derivative of natural log would give us a 1 over x, and there isn't one of those. So while slices are easy to set up, they're horrible to have to integrate. We don't have the tools to do this yet. All right, so then let's change our perspective here and think about one of the cylindrical shells. So I'm going to make use of this slice that I already drew and show you the cylindrical shell that it goes with. Okay, so there would be one of the cylindrical shells. I'm going to change color just so you can see a second one. We'll make another one. How about we'll make a taller, narrower one. Okay, so there are 2 examples of our cylindrical shells. And so let's set this with shell method. So with the shells method, we need to do 2 pi r times h, and then multiply that by our thickness. Now in this case, we'll start with our 2 pi. The thickness is going to be a dy, because the thickness of the shells is in the y direction. So we need to get the radius and the height. Now the radius is nice. It's the same as before. It's just y. So then the question is, what about the height? Well, these shells, the rightmost is always on x equals e. And the leftmost is on the natural log, right? So we need to have the difference in those two, but we need the difference in their x's. We need these as functions of y. So the first thing we're going to do is take this equation and solve it for x. All right, so we're going to get y divided by 3 equals natural log of x. Let's take in this guy. And then to solve that for x, we need to use e. And that gives us x equals e to the y over 3. All right, so our height then is going to be the difference in those. It's going to be e minus e to the y over 3. So just to sort of remind you what all those things are, this is 2 pi r and h. Okay, so we have our 2 pi r h. All right, and I see Danielle made it in. Yay! Welcome, Danielle. I'm glad you were able to get in. We're just looking at a homework problem, number 8 from the cylindrical shells. All right, so here's our 2 pi RH. All right, now we're still not quite done with this integral, right? We need our bounds, but those are going to be our y values. And we already know our y values go from 0 all the way up to 3, because that's what we got when we plug in these. So it's 0 to 3. So let me just make this a little bit nicer. This now, if we look at it, it's going to be 2 pi times integral from 0 to 3 of e times y. And this e is just a number. It's not a function. It's just e. And then the other one's going to be minus y times e to the y over 3 dy. All right, so this integral that we've got in the orange is going to give us the same value as the integral over on the other side that's in black. And if we look at the one in orange, this one's going to be a little bit easier to integrate. Like the e times y, that's no problem. E is a constant, the y gives us y squared over 2. This one we got y e to the y over 3. Well, that's going to want us to do some sort of a u substitution, right? Let u equal y over 3. But to be 100% honest with you guys, you don't know how to integrate this yet. We need a method called integration by parts. But this is at a point where we can easily plug it into something like Symbolab or your calculator and whatnot. So when it comes down to it, to actually get the volume, either one of these is totally fine. They're going to give you the same volume. It's just pick your poison, right? Which one do you want? What I'm most concerned about right now is how do you guys feel about constructing your cylinders? Are you visualizing them? Are you able to see the respective pieces, the R's and the H's?
Yeah, I think I can set them up pretty good, but sometimes I do have a little trouble visualizing them.
Yeah. And those come with practice, right? The more of them you do, the easier they're going to come. Yeah. Anyway, so is that better for that one?
Yeah, thank you.
Yeah, that's one of them where the way they gave you the equation isn't particularly useful for the shell method. We had to go ahead and solve for the other letter, and you'll often see that if slices want your function one way, the shells are going to want it the other way. Solve for the other letter. So that's something that happens quite a bit in these kind of problems where you have to solve for one of the other, or not one of the other, solve for the other variable and get it as a function of y, like in that case. All right, cool. Any other homework questions, or we're feeling in general all right? And you probably noticed that there were some homework sets that I pushed the dates out on. Edward reminded me over the weekend. He's like, hey, we haven't talked about this stuff. Is it really due Monday? No. So like the arc length and stuff got pushed back, just FYI. All right. So are we ready to start talking about some other uses of integrals, specifically arc length and surface areas?
We're ready.
Yeah, sounds good. All right. So I'm going to hop up to my whiteboard. I'm sure you guys saw there's a second screen here. I'm going to go ahead and switch to that. So give me 1 second and you'll see me up at the board in just one moment. All right. So hopefully you guys should be able to hear me. Everybody hear me? Thumbs up?
Yeah.
Yep. All right, cool. All right. So let's talk about some more uses of integrals, some other things that we can do with them. And the next thing that we're going to look at is arc length. So imagine I gave you this like really easy question. We all know the parabola really well, right? So imagine we've got just good old y equals x squared. But what I want to know is how long it is from 1, 1 to minus 1, 1. Okay, so this is just good old y equals x squared. And I want to know the length of the curve. I don't mean I want to know the distance between these points because I know the distance between, right? If I just draw the straight line across, I know that I've got a length of 2. That's not what I'm curious about. What I'm curious about is how long is this? Like if this was a rope that's dangling between 2 points here, I'd want to know how long is that rope. So it's a pretty easy question, right? It's not a complicated idea, but trying to figure out the length would be tricky. Think about if you were doing this for realsies. Like I said, hey, find the length of this. Could you do it? Like, can you think of a tool you could use to figure out the length of this curve?
I mean, maybe with like trig.
Okay, so maybe with some trig. I was actually thinking of like a physical tool, but because like, how about this? What if we just took measuring tape, something that is flexible, or we take a piece of string and we lay it on there, and then we straighten out the string or something like that. So in reality, it might not be that difficult to figure out the length, but mathematically, it gets a little bit challenging. And Bree, you just mentioned, well, maybe use some trig. Well, trig is great and all when we have triangles and nice straight things, but this isn't straight, right? This isn't a line, it's a curve. So the question is, can we somehow figure out how to do this using calculus? And the answer, of course, is yes. So let's just back up. What if instead of giving you those 2 points, or that distance, what if I just said, we're going to change this. So instead of a parabola, what if I just want to know the length of the line segment that connects the vertex 0, 0 and this point 1, 1? Can you answer that?
Yes.
Yeah. How do you find the length between 2 points? Excuse me.
Don't you use like the slope and then sorry, I'm blanking out. It's harder to do this at home.
You're definitely thinking right. It's not the slope that
The
we need.
midpoint or something.
We use the distance formula,
Oh, that's what it is.
right? And so we know the distance between any 2 points is given by the difference in x's squared and the difference in y squareds. We add those up and we take the square root. And so this right here is this is the distance formula. And it actually comes from the Pythagorean theorem. If you look at the right triangle, like you think about this blue segment right there, if you were to draw the right triangle, these 2 sides are the lengths of the difference in x's and the difference in y's. And then if you just use the Pythagorean theorem, good old a squared plus b squared equals c squared, there you are. All right, so between any 2 points, you can find the distance between them using this formula, right? And maybe a better way to think about it, or maybe not better, but we're going to be a little bit lazier, so we don't have to write out as much. We'll just call this delta x squared and delta y squared. Right, so if we know the change in the x and we know the change in the y, you square them both, take the square root of the sum, then you got your distance. All right, so 2 points, we know what to do. Well, let's come back to this idea of the parabola and say we want to find the length of that curve. Now I'm going to zoom in a little bit just so that we can kind of see better what I want to show you. So here's just a portion of it. Let's say we're going to look at this portion. So what we could do to approximate this is draw a whole bunch of line segments, like just break it down into pieces, kind of like what we did when we were looking at areas under the curve. And so you go, all right, well, what if I just go from this point to this point, and I'm just going to split this into a couple intervals with some points on it. So hopefully you guys can see all those dots. And what I could do is just connect those dots with line segments. And even with what I have right here, you can probably see that the total length that we would get if we added up all those line segment lengths is going to be pretty close to what the actual curve is. And it's probably also really clear that the more of these line segments we have, the smaller that they are, the better the approximation. Well, if this is feeling kind of familiar, it should, because this was basically what happened with areas. We started by saying, all right, well, let's just approximate it with a handful of rectangles that are easy to find the areas for. We saw that it was a decent approximation, but it got better as we had more of them. And then we went to well, let's just take a limit so that we have an infinite number of them. And the next thing you know, we have an integral. Well, that's what's going to happen here. This is going to turn into an integral because we're adding up all of the line segment lengths until we have basically an infinite number of them. So it's exactly the same approach. It's just this time, instead of adding areas, we're adding arc lengths. All right, well, let's come back to the arc length idea. So if we're going to really break this down and do what we kind of did before, let's actually set it up with the limit and all that kind of thing. So we're going to start by taking a sum of a bunch of things, and those things are going to be the arc lengths. They're going to be the lengths of those line segments. And then we're going to take a limit as n goes to infinity of that, because we're going to want an infinite number of them. We want them really, really small. Okay, well, let's look at what the arc length is going to be. So each of those line segments is going to be a delta xi squared plus delta yi squared. All right, so you guys all good with that? The delta xi is just going to be the x difference on these 2 points, wherever we happen to be. And then the delta yi is the y difference. But for each one of them, we're going to calculate this square root. And then add them all up. All right, so that's what this thing looks like. Excuse me. Now let's manipulate it. So I'm going to take this square root and actually divide out the delta x squared. So here's the algebra on this. We get delta xi squared times 1 plus delta yi squared over delta xi squared. So I just divided both of them by delta xi squared, and I just see that I went into the glare spot from my window. I apologize for that. Let me now pull out this delta xi squared. I take the square root of it. The square root of a square cancels. So what I'm left with is a delta xi times the square root of 1 plus delta y I squared over delta xi squared. So just a little bit of algebra gets us here. So
In the original equation, that's delta x sub I squared plus what squared?
delta yi squared.
Okay, thank you.
Yeah, you're welcome. I know, yuck, right? This is really gross looking. But it turns out this is going to get really nice really fast. Because let's do this limit sum business. If we do the limit sum business, we know that this turns into calculus, right? And so think about what happens here. This turns into an integral. It's going to be from A to B. So in this case, like this would be A, and over here is B. So we're just integrating from A to B. The delta xi, that gets really, really thin, which means that becomes our differential. So that guy's going to become the dx. I'm going to go ahead and put that over there. But again, that's coming from the delta xi. Excuse me. Now, this other piece, there's going to still be the square root. And inside that square root, there'll be a 1 plus. But now I want you to think about what delta y over delta x becomes if they get infinitesimally small. Anybody recognize what that becomes?
Well, it's either 0 or infinity, I think.
It's actually neither one of those. I mean, it could be one of them. But just think about this. So the delta x. So let's write these. This is going to become a dy squared over a dx squared. And what is dy over dx?
So the slope?
It's the slope, which in calculus is the derivative. So check this out. This actually becomes f prime of x squared. The dy over dx is really, it's your slope, so it's f prime. And then that quantity is being squared. So it turns out that this is your arc length formula. So let me just go ahead and write this so we can box this up. So this is your arc length. It equals the integral from A to B, from where we're starting to where we're ending, of the square root of 1 plus the derivative squared. I think this is kind of beautiful, actually, in how it gets built, because we just start with distance formula, and the distance formula is gross and yucky, but you do a little bit of algebra and then let the calculus happen, and it turns into a really nice form. So if you ever want to find the length of a curve, all we got to do is integrate the square root of 1 plus f prime squared. All right, well, let me show you how this gets set up with some specific examples. All right, so let me come over here and show you one. Let's actually go back to that original question where we were looking at f of x equals x squared. And we were going to go from x equals -1 to x equals +1. That was the very first one that I introduced to you. And I said, hey, let's try to answer this question. All right, so in terms of the picture, right, we're basically trying to find the length of that part of our parabola. So let's set it up using the arc length formula. So this is going to be arc length equals the integral from -1 to 1. Right? We're going from -1 over to +1. The square root of 1 plus and now what we need is the derivative of f. So what's the derivative of f here?
2x.
2x, beautiful. All right, so we're gonna have 1 plus 2x, that quantity squared, dx. All right, so -1 to 1, square root of 1 plus 4x squared, dx. And there it is. You do that integral, and you're going to be able to figure out the length of that curve. I don't know. At this point, a lot of times people feel like, wait, that's it? There isn't more to this? No, there is no more to this. If you ever want to find the length of a curve, you take its derivative, square it, add 1, take the square root, and integrate from a to b. That's it. However, with that said, think about trying to get the integral of the square root of 1 plus 4x squared. And that's one that we don't know how to do yet. You have to learn this method called Trig Substitution, which we'll learn in the next chapter. So even though this is nice in terms of setting it up, it often leads to things that are really hard to integrate. And you can probably see why. We're always going to have a square root of stuff, which means the only technique we have right now that will work for us is to do a U substitution. And it's very unlikely that the stuff that's on the inside, that there's going to be anything on the outside for it. So just realize that that is one of the issues with this. It's just the thing that you're going to end up integrating can be a little bit gnarly, and we don't have the techniques. However, with that said, we do have technology that helps us. So this is one of those where when you're doing your homework, for sure it's fine to rely on things like Desmos and Symbolab and your calculator and all that to do these integrals, because we don't have the ability to do them yet. All right. So then you might be going, well, why are you showing us this before you show us how to do that integration? Well, I'm trying to show you some more applications, because otherwise we're just doing integrals for the hell of it, and it helps us to have a reason behind it. All right, well, that's all you got to do. It's just a question of what is your function and setting it up. So let's do some more just setting them up. I'm just going to leave this for where it is right now. If you want later sometime, I'll be happy to use my calculator to get the answer for you. But it's basically, you know, a plug and chug. So let's try another one. How about this function? So this time, let's go with y equals sine of x. And we're going to go just from x equals 0 to x equals pi over 2. So again, you guys all know what this looks like. And for sine of x, looks something like this. And if we're going to go from 0 to pi over 2, 0, of course, is our intercept. And then where's pi over 2 on this graph? You guys remember for sine?
Is it the top of the first loop?
Yep, it's at the top of that first hill right there. Perfect. Thanks, Tiana. Oh, and welcome, by the way. I didn't notice that you joined us. Okay, so there's pi over 2. So we're basically just looking for the length of that piece right there. Cool. Can you imagine an application where you might care about that? And if you can't, that's all right. I'll just tell you that sines and cosines show up all the time, and so knowing lengths of portions of them are kind of a big deal. But let's go ahead and set this thing up, see what this looks like. All right, so to get this arc length, we're going to integrate from 0 to pi over 2. We need the square root of 1 plus the derivative of this squared. So what's the derivative of sine?
Cosine?
Cosine, beautiful. So it's going to be the square root of 1 plus cosine squared x dx. All right. Again, punch this into a calculator and you'll get your value. But you can again see that trying to integrate this thing is going to kind of suck. Right? It's not gonna work out very well for us with the methods that we know right now. Yep. That's all I can say right now. Yeah. All right, so how are we feeling about at least being able to set up an arc length? Not too bad?
Yeah, not bad.
Not bad. All right, let me show you one more thing about this though that makes this even better. Even better. Remember when we would be doing some sort of a volume kind of deal, and we would have to maybe now rotate such that we had to figure out the function as a function of y instead of a function of x. You remember those, right? Where you have like, think about that homework question you guys asked me about earlier, where we had the y equals 3 natural log of x and we had to solve it for x. When we turn things sideways, sometimes it's a little complicated, right? Like instead of y equals sine of x, what if I had said, let's do exactly the same thing, but this time we're going to look at x equals e to the y plus 2. And we're going to go from, say, the point, I'll even give you some points here. Let's go from the point 3, 0 to 2 plus e, 1. And I know I really, really just bugged you a lot by giving you a point that was 2 plus e, 1. But that is the x value that corresponds with the y of 1 when we have this equation. Okay, so exactly the same kind of question as before. I gave you a curve, and I gave you the endpoints, and I want you to figure out its length. So before we actually set it up, let's draw the picture for it. So I'm just curious, does anybody know what x equals e to the y plus 2 looks like?
No.
No, okay, thank you. This is what
I was
you're
gonna
doing in class.
say something
I've been able
similar
to see all your eyes with the glazed over, and you're like,
I was gonna say probably something similar to what y equals e to the x plus 2 looks like,
Okay,
but
so
on its side.
yeah, we can go back to the think about what it looks like as with the y's and x's are swapped, and then do that whole like, okay, we'll rotate it kind of business. So I appreciate that, Douglas. Thanks for mentioning that. If you think about e to the x plus 2, but then we flip it, well, what this is going to look like is something along the lines of this. So it's going to look something like that. And so the points I just gave you, 3, 0, that's this point. And then 2 plus E, E is around 2.7, right? So add another 2, it's around 4.7. Yeah, that's something like that. So I'm basically asking you to figure out the length of this curve. All right, so that's what it looks like on our picture. And I know it's horrible that I gave it to you in this way, but I did it on purpose. So let's just think about what we would have to do if we were going to set this up. We would need to know our x bounds, which we've got. If you come back over here, our x's are the 3 and the 2 plus e. So we've got our x bounds. But then we'd need to know this thing as a function of x. We'd actually have to solve it for y and then differentiate it. All right, well, I mean, we can do that. It's just I would rather not do that. So check this out. We might want to go to the, all right, well, let's just change our perspective. Instead of thinking this as a function of x, what if I wanted a function of y? Well, it turns out that if you want to do this as a function of y, you can also think of your arc length as an integral from a to b, the square root of 1 plus, I'm going to call it g prime of y squared dy. It's actually exactly the same format. Exactly the same format if we have a function of y. So before I show you why that works, let me show you how fast this is to set up then. So what we would need to do in this case is instead of solving this thing for y, we just differentiate it where y is the variable. So the derivative of e to the y plus 2, let's think about this x prime, is just going to be e to the y. And so this one, we want to find this length. It's going to be an integral of the square root of 1 plus e to the y squared dy. And we would need our y bounds. Well, our y values were 0 to 1. So there you go. So if you're given functions of y, okay, you don't do it any differently. You differentiate that thing, but thinking of y as the variable. Take that derivative, square it, add 1, put it in the square root, and integrate your bounds. So arc length is actually kind of nice. It doesn't matter whether you're thinking about it as a function of x or y. Now, I do want to show you why that happens. But if you think about it, it really shouldn't matter, right? If I'm just talking about this curve, whether I'm thinking about it as how y changes with x or x changes with y, it shouldn't really matter. And you can algebraically see it if you go back to the arc length formula. Remember what we had was the square root of delta x squared plus delta y squared. And what I did was I factored out a delta x. Well, now instead, let me factor out delta y. So if I just real quick do this algebra. All right, so here's my delta y. I pull that delta y out. Now take your limit, make everything really small. That delta y becomes the dy. This delta x over delta y, that's the derivative of x with respect to y. So that's your g prime. And you can see you get exactly the same form. So arc length is kind of nice because if you got something as a function of x instead of a function of y, so what? You don't do anything differently. All right, so arc length, easy to set up, super hard to actually integrate. because the forms are kind of nasty. But there's another application that we can use integrals for. All right, so before I jump to the next one, any questions on what I just did here?
No questions on what you just did, but if we're gonna have these problems in like a test or an exam and we don't know how to integrate them, will you allow us to just plug the integral in on our calculator?
Absolutely. Yeah.
Okay.
This is going to be the kind of question that would show up on a calculator portion of an exam.
Okay.
Absolutely. Yeah. No, I'm not going to make you integrate something you don't know how to integrate without calculator. So, oh, and speaking of the exams, I do have them graded. I haven't entered anything in yet because I wasn't sure how things were going to play out today. So expect to see those scores in later today. So just FYI. All right, so let me show you another application that's really related to arc length, and that's surface areas. All right, so here's our next topic. Let's look at surface areas of revolutions. Let me put surface areas of solids of revolution.
This section does center on arc length, though, right?
I'm sorry?
This section does center on arc length?
It's both. The section is both arc length and surface areas. They're in the same section.
Okay, thank you.
You're welcome. All right, so basically what we're doing is we're taking something and we're rotating it and now looking for the surface area. So think about when we were doing this before and we were finding the volumes of these shapes. Now we're finding the surface areas. So again, just imagine, let's just take y equals x squared because it's a really useful guy. So let's say that this is y equals x squared and we're going from 0, 0 to 1, 1, but we're going to rotate it about the x-axis. So you remember what kind of shape this was? This was the one that, like, I called it the thorn, like the rose thorn. I think maybe Brianne was talking about it was like a trumpet horn or whatever, right? So it looked like, if I kind of extend it out here, here's the other side, and then we just do a little circle, right? So that's the shape that we were looking at. And what we did before was find the volume that we would get from the shape. But now what I want is just the surface area of it. Right? What is the area of the outside? The way to think about this would be like the volume. This is how much paint we would have to pour into it to fill it up. The surface area is how much paint we would need just to paint the outside. Right? So it's a different amount. But this one is just, we want to know surface area. All right, so the idea behind this is going to be the same as everything so far. Is what if we were to break it down into smaller chunks of area? So I'm just going to draw a couple of dots here that correspond to just breaking this interval up. And if I were to kind of break it into these pieces, here's an example of one of them. Let's look at this guy. And I just connected the dots. What I'm going to get, if I redraw that here, but kind of exaggerated. So I'm going to get this. So hopefully you guys can all see that shape if I rotate it as what I'm getting from my piece. And each of those pieces is going to look like this. They're just going to have different sizes, different radii, but I kind of put those together and it would approximate this bell. So if I can figure out the surface area of this shape, then I could take its surface area, add it to the surface area of the next one and the next one. And that's going to give me my approximation. That approximation will be better as I do more and more of them. And then if I actually make it so that I've got an infinite number of them that are super, super thin, then it's exactly that surface area. All right, again, if you've seen this story before, or if you think you've seen this story before, you have. That's integrals. Integrals are adding up lots of little things. So basically, all we need to do in order to solve this, or get a, figure out how to do this in general, is we have to be able to determine the surface area of that little chunk. Now, I'm going to tell you what this is called so that when you're reading the book or you're looking at a homework problem where they mention this word, you know what it is. This is actually called a frustum of a cone. Okay, so frustum of a cone. Basically, just think it's a cone whose top has been sliced off. Right, so there's our cone, and we slice the top. So this is called a frustum. I'm not going to use that word ever again, probably, but I want you to know it just so that when you see it, okay, that's what they're talking about. All right, so we need to know the surface area of the frustum of a cone. Well, if you look at that, you can kind of imagine that it's sort of like what we did when we had cylinders, where, remember for a cylinder, how we got the surface area? Yes, hopefully.
Yeah.
It was just the thing about a cylinder is just a rectangle, because you can take that cylinder, break it apart, right, and flatten it out. And that rectangle, its area was its height times the circumference of the circle. So it was good old 2 pi r times the height, 2 pi r h. So we used that when we did the cylindrical shells method. Well, we can kind of think about this the same way, except this side isn't just vertical, so we can't just be 2 pi r h, because there's a little bit of an angle to it. But if you go through it, and I'm not going to do this, you can see the derivation in the book. I'm not going to go through the horrible algebra on it. But basically, what it comes down to is it's that same kind of 2 pi r business, but then we multiply by the length of this side, like the actual distance that we need to travel from one point on it to the next. Okay, so this length right there. So we're going to do 2 pi r times that length. And then we need to do 2 pi r times the other length and the other length, and so on. And if you piece that all together, what we end up getting is this formula right here. Okay, so
Basically, it's just 2 pi r times arc length.
it's going to be 2 pi r times the arc length. Yeah. So the formula for it is going to be an integral from a to b. We're going to put here 2 pi r times the arc length. So there's kind of our general in words formula. And that arc length is the same arc length that you saw before, where this is going to be the square root of 1 plus, and I'm going to go ahead and just put f prime squared. I'm not going to put the letter x or y, because it can be either one, like we saw, but that's all we're going to have to do. So you can now see why this is incorporated in the same section, because it's very dependent on arc length. It's the exact same approach. It's just now we have to multiply by a 2 pi r. So let's come back to this one. And let's see if we can do this for y equals x squared. All right, so that's the picture that I've got. And in terms of the arc length, and do we want to do this x's and y's, I definitely would do this with x's, just because it's already as y equals, and it's going to be pretty easy to do. Let's say we're again going from 0, 0, and we're going to come out here to 1, 1. So let's start setting this up. So our surface area is going to equal the integral from 0 to 1. Those are the x's that we're going. I need a 2 pi, but now I need to know r. Like, what is the radius for each of these little slices or each of these little chunks? Well, let's just look at it. What determines the radius of this guy? I drew it in there in green.
The x value
Not the x value.
from the y equation, the x squared.
So it's the
X.
y value, right? So it's going to be 2 pi times y. We'll replace that in a second. And then the arc length is going to be 1 plus 2x quantity squared dx. But the y is actually the equation x squared. So here's our surface area. The formula is going to be 0 to 1, 2 pi x squared times the square root of 1 plus 4x squared. So before we actually try to integrate this or even think about it as an integral, do you see the setup? 2 pi r times the arc length. In this case, the r is the y. And if we rotate one of these things about a coordinate axis, either the x-axis or y-axis, your r is either going to be x or y, depending upon which one. And we kind of saw that when you're doing the cylindrical shells and volumes by slices, because it's kind of the same idea. It's the same, radius is still working the same way. We're just doing something different. All right. So this guy, now the question is, all right, well, we got it set up. How are these going to be when it comes to integrating? Well, these are going to be better than just arc length, because now we are going to have stuff on the outside, and that stuff on the outside is going to give us the potential of being able to do some sort of a U substitution trick. All right, so we do have that going for us now, but in general, they still are kind of nasty in terms of their integration. So this will definitely be another situation where, yes, if on an exam or a quiz, you're definitely going to be able to use your calculator to do them. But at least the structure is nice, because it's always the same thing over and over and over. All right, so what do you think about these so far? Not too bad.
When you were drawing the, I forgot the name of it, like a frustum or something.
Yeah,
It
frustum,
had two different sizes of circles, but when you set up this equation, you only use the circumference of one circle. Why is that?
Okay, that's a really good question, Tiana. I'm glad you asked. So why do you think I can get away with just one circle? Anybody have an idea? Only one of the radii instead of both?
For the same reason we can just do slices.
Kinda. Let's just think about what I'm doing with those. I'm gonna, when I turn it into an integral, what's happening to this little frustum?
You're adding them up consecutively. So when you put in an integral, the next radii will be a part of it because you integrate the function that determines the x or the radius, not the x, the radius.
So you're right that I'm adding them up, Brian, and that's definitely true. And how the radius of one, like the bottom of one is the top of the other, right? They kind of fit together. But that's not actually why I was able to do that. What's the other part of integration? Not just adding up, but what else am I doing? Like, go back to just areas under the curve. I was adding up a bunch of rectangles, right? But what else happened to those rectangles? And I'm trying to give you a hint with my fingers like this.
Because you got the area of each of them specifically.
They have the same thickness.
Okay, so they all have the same thickness. What happens to that thickness?
It's infinitesimally small.
Yeah, they get really, right? Like incredibly thin. So now let's think about a frustum of a cone that gets really, really thin. So this is exaggerated, right? But here's the frustum. Now, if I start making it thinner, so there you go. So it's thinner. Let me make it thinner again. Okay, so now I've gotten one that's getting pretty thin. What's the difference in those two radii? Or what's happening to those two radii? Those two circles are getting closer and closer and closer to the same size, right? So you can imagine if I keep going so that they're infinitesimally thin, right? Like thin, 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 thin. Radius on the top and radius on the bottom are going to be basically equivalent. So that's why I can just say, well, I'm just going to take the radius of this. Because pretty soon you can't tell the difference. So does that kind of make sense, Tiana?
Yeah, it does. I was just trying to relate it to the arc length because the arc length feels like we're using 2 points. But I see what you're saying.
Yeah, I can totally appreciate that. It's just it's a slightly different viewpoint. And if you actually go through the algebra, which I told you I wasn't going to do, and I'm still not gonna, but if you look at that in the book, you can see where that it comes down to just the one radius. Because you can do sort of a to the big side versus the small side, you're going to have r plus a little bit and then r minus a little bit. And when you multiply those together, you get a difference of squares, right? Like think about this. If I have r plus delta x times r minus delta x. So think of this r is the r that I'm using in the middle, right? The middle r. And then I'm going to have a little bit of an increase and a little bit of a decrease for the bigger versus the smaller. And if you do things like you multiply them, you get r squared plus a bunch of stuff with delta x's. And those delta x's would go to 0. So that just looks like r squared. So that would be like an area argument. When you do the area of a front, the circle,
I don't know if it's just me, but I can't hear you.
It wasn't just you. I couldn't hear you either. I still can't hear him.
Yeah, okay.
I don't think he can hear us either because he's still talking and I can't hear him.
those delta x's end up canceling and not mattering.
Oh, I can hear again.
Right? Did you guys lose me for a second?
Yes.
All right. Sorry about that. Where did I lose, or where did you lose me?
Like
Maybe
the whole-
back up like
Well, that was, I had like 4 people saying something at the same time, so I caught nothing. But here we go. Long story short, I can use just radius because they get infinitesimally small. There's algebra behind it. But I think also you can just kind of imagine if they're getting really, really thin. Yeah, radius on top and radius on the bottom are so the same that we just call it radius. Anyway, let me thank you for letting me know that you lost me, by the way. Yay, internets. Right? All right, so let's set up some more of these. Let's actually set up a few more integrals. We're not going to necessarily do them, but we'll practice going about different axes and things like that. So let's try this guy. let's do y equals e to the x. We're going to rotate about the y-axis. And we'll just go with x is between 0 and 1. And what we're going to do is we're going to find the arc or the surface area. All right, so let's see if we can get this thing set up so that we can calculate it. All right, so y equals e to the x between 0 and 1.
Sorry, did I miss something about the integration of the last example, the one with the x squared?
I didn't do the integration.
Oh,
That's
okay.
what you mean. Right now, I'm just getting them set up, Douglas, because these are things that most of them, like including that last one, we don't have the techniques for doing yet.
Okay.
So we are going to have to rely on technology to help us at this point
Right.
until we learn some other techniques that are coming in the next chapter.
Okay. Thank you.
So you didn't necessarily miss anything, but if you were looking for what's the answer, I'm not giving you the answer. I'm just getting it set up to a point where we can do the answer. Does that make sense?
Yeah. Thank you.
You're welcome. All right, so e to the x between 0 and 1 for x is going to look like this. So there's the piece that we're going to rotate. We are going to rotate that about the y-axis. So here. So what that would look like is basically like that little bowl. So we're looking at what is the surface area of that bowl. All right, so here is one of the typical conical pieces here. Gonna look like that. So let's think about this in terms of the 2 pi r and the arc length. Now, because we're doing arc length, we could actually do it in 2 different ways. But the nature of this is such that we know which differential we want, whether we want a dx or a dy. And it all comes from these little conical slices. So which are we going to want, dx or dy? Which way are we adding in this case?
dx. I mean dy.
Let's say we have a vote for dx, but that dx vote got turned into a dy real fast. What do you guys think, dy?
I'm also saying dy.
All right, so we got.
Oh,
right.
wait, I guess looking at the equation, it looks more like dx.
Okay, so the equation suggests the equation. But think about the slices, and when we're adding them vertically, right? Like here's one of my little conical sections. There's going to be another one vertically, another one. And so this is definitely telling me I want a dy. Just like when we did slices, like if you look at this picture and you think about volumes, if you're more comfortable with that, and you go, ooh, I want to do this volume with those slices, so that's a dy kind of slice. It's also going to be a dy kind of surface area. Okay, so in general, and I think I kind of made this comment with, well, with one of the volumes, I don't remember which, but if you rotate about a vertical axis, when you're doing these, you want a dy. Around a horizontal axis, you're going to want dx, just in general. In fact, let me go ahead and write that up over here. So vertical axis, There's going to be a dy horizontal axis. You want a dx. Okay, that's just here in general when you're doing surface areas. Just like that's the same as doing volumes by slices. All right, so we're going to go with dy. So if we start setting this up, we're going to want this as a dy. So let's start getting what we need. So we need 2 pi times our radius. So what's going to give us our radius here?
The function.
All right. It is going to be out to the function. And since it's, again, the coordinate axis, that radius right here, if we think of this as our r, the r is actually going to be whatever the x coordinate is on our function. Right, so it's actually in x. So I'm going to write this as 2 pi times x. And then we're going to need our arc length. But I'm going to want this in terms of y. So I'm going to write here f prime of y squared. Okay, so that means that I need this thing as a function of y instead of a function of x. So I am going to have to solve it for x. But that's a pretty quick solve, at least it should be. What does this become if I want x equals? If y equals e to the x, what does x equal? He says hopefully, but now starting to be concerned about the question.
The radius.
Well, it is the radius, but I want to know specifically for this function. I solved this for x. X equals what?
Oh,
It's going to be natural log of y. Because e and natural log undo each other. Yeah, no, maybe, kind of, sort of. All right. So x is equal to the natural log of y. And that is going to give me my radius as I move around with my y's. Right? As my y's get bigger, my radius gets bigger according to this. Okay, so here's that integral then. We're going to have 2 pi. X is natural log of y. And then in our square root, we need 1 plus the derivative of this squared. So in terms of y, if it's natural log of y, what is the derivative?
1 over y.
1 over y, beautiful. So this is going to be 1 over y, that thing squared, dy. And then we need the bounds on y. Well, I gave the bounds on x's. Son of a... All right, if I'm going to get the bounds on y, I just need to plug these things in. So if x is equal to 0, what is y? What is e to the 0?
1.
1. Thank you. I just saw Danielle throw up the single finger, and I'm glad it was that finger as opposed to another one. What about x equals 1? What's y equal?
0.
What's y equal? So we plug that in, we get e to the
0.
1, which is e. All right, so there is the setup for this integral. And realize that this one's going to be really gnarly if we have to try to do it by hand. It's going to have to use what's called integration by parts, and then probably some other stuff in there. But Symbolab, T89, whatever, it'll do that without even thinking about it. All right, so there's the setup for that guy. So it all comes down to the same as before. we need to figure out the radius. Just like we had to figure out the radius for volumes, we have to do that for surface areas. We're just using a different formula now, right? We're doing 2 pi r times the arc length. All right, so beyond that, where these can get a little bit worse is if we rotate about a non-coordinate axis.
Where did we get the 1 over y squared from? Because
So y was the derivative of this. If I differentiate, so we'll call it x prime. X prime is 1 over y.
oh, okay, I see. We were doing f of y, not f of x. Got it.
Yeah, and so and that's why I at the very beginning I went, hey, what's our differential? Is our differential a y or an x? Because that matters. Like that kind of drives everything. So I recognized that this was dy, which meant I needed everything as functions of y, which then led to solving this for x and differentiating that and blah, blah, blah. But good question. Any other questions before we move off of this one? All right, so let's do one more here, but this time let's rotate about a non-coordinate axis. So let's try this. Let's go with, try to do a function we haven't done yet. We pretty much hit all the big ones. All right, well, let's do this. Let's rotate y equals cosine of x about the line x equals 1, or no, y equals 1. And let's find the surface area between, on the interval 0 to pi. So we're gonna have our x's go from 0 to pi, so we'll take that piece of cosine and we're gonna rotate that about the line y equals 1. So I'm gonna start by drawing the picture. So we all know what cosine looks like. But I'm only going to draw it between 0 and pi because that's the only piece that matters to us here. So at 0, we're up at +1. At pi, we're at -1. It does something like that. Okay, so there's our graph of cosine. And we're going to rotate it about y equals 1. And y equals 1 is right here. All right, so we all see the picture, I hope. I'm going to go ahead and kind of give you what it would look like if we complete the whole picture. So you would see something that looks like that, except that's better. All right, so that's the shape that we're seeing. I think this kind of looks like a Hershey's Kiss.
It
So-
definitely does.
So we're looking at what is the surface area of that. All right, so are we all good with the picture? Now
Yeah.
let's start setting up this integral. So again, I'm going to draw one of the little pieces, one of the frustums, so that we can kind of get an idea of first which direction we're going, if we want a dx or dy, and then we can start figuring out radii and all that stuff. Okay, so do we want dx's or dy's?
dx.
Yep, this is going to be a dx because we're going in that direction. Or we can come back to, we were going around a horizontal axis, so we're going to use a dx. Okay, so let's just start setting this thing up. All right, we need 2 pi RL times a dx. All right, well, we'll do a couple things. I'm going to pull the 2 pi out because those are constants, so might as well just get them out of the integral. I can do my bounds now. I know for sure my x's are going to go from 0 to pi. So now I need to figure out the radius. So what is the radius of this frustum?
Y.
So it's going to be a y direction, but it's not just the y coordinate. So let me actually erase this other piece real quick, because I want to come back to the function that we were given, which is this down here. So here would be our radius. That kind of little red line I put right there. I need to figure out that for our radius. Now, it is going to depend on the y of our function, right? Because as we're moving along, the radius changes because the height of our function changes. So how does that radius relate to the y coordinate?
The cosine.
So the cosine is giving us the y coordinate. Let me help you out a little bit. Let me put this here. There's our y value.
Oh, that's right. It's not rotated about x. It's rotated or the axis. So would it be cosine plus 1?
All right, you're getting close. You're getting very close. Just look at this relationship here real quick. I mean, we've got the r plus the y. So the r is this above the curve and y is below. Those two together equal 1. Because that's where my axis of rotation was. So my r is going to be 1 minus y.
I see.
All right, but then what's our y? Well, the y was the cosine of x. So our radius is going to be 1 minus cosine of x. And if you just do a couple of x values, you can see that this works. Like at the beginning, when x is 0, cosine of 0 was 1, and we get a radius of 0. Okay, yeah, 1 minus 1 is 0. As we move along, like when we get to this point where cosine is equal to 0, the radius is equal to 1. When we get to where the cosine is equal to negative 1, we have a radius of 2, 1 minus negative 1. So that little mental check I just did is something I do all the time when I'm setting up these R's, just to make sure that it's doing what I want it to do. All right, so there's my R, and then I need my arc length, but I need my arc length in terms of x. So I already have my function in terms of x. I've got y equals cosine, so I can jump straight to its derivative. Its derivative is negative sine. We'll take negative sine of x and square it, and make that a dx. All right, so there's the integral. There's the integral that's going to calculate the surface area of that Hershey's Kiss. Whew. It's ugly looking, but here's the thing. Once we've got the integral, we're good. Right? We just did all the work, because now we've got technology that can take care of it for us. And even if we wanted to do it by hand, this is the majority of the work, is getting us to a place where we can integrate. Because without that, we don't know what to integrate. We don't know how to even start. Now we got it. All right, so there's surface areas. So think about what we did today. We just did two more types of things. One was arc length, and the other was surface area. And yeah, surface area is related to arc length. But really, here's what I want you to get out of this, is that we added up a bunch of really tiny things. Those things that we were adding are different now, right? They're lengths of line segments. They're surface areas of frustums of cones, whatever. But the fact that we end up adding up an infinite number of really, really thin ones turns it into an integral. And that's kind of the whole point. All right, so anything out there in the world that we can approach by adding up lots of really, really small things is going to lead to an integral. And so what we're going to do on Wednesday is I'm going to show you some physical examples, some things from physics where we're adding up lots of little things that lead to integration. All right, so that's kind of what chapter 2 is all about. Chapter 1, we introduce you to integrals. Chapter 2, we're showing you where you use them. Chapter 3, we're going to give you more techniques to solve them. All right, anyway. So I think I'm done at this point, but if you guys have any questions, I'm willing to discuss them. Anything at this point that's kind of cloudy about what we talked about today? No? Okay, so the plan for the rest of the week, as of right now, unless I get some other direction from the college, is that we're going to just do this the rest of the week. I'm supposed to stay out from the college at least 5 days after a positive test. So that's the rest of this week. So we'll plan on Wednesday and Friday doing it this way. I know it's not quite as good as being in the classroom, but it's not terrible. And I figured it would be better than trying to get subs. Plus, there was no way they were going to get a sub for you this morning, over the weekend. So like I said, unless I hear otherwise, we're going to do this. I'll keep you guys informed through Canvas, so keep your eyes open for announcements. And all my office hours are just going to be on Zoom. Go ahead and use that link that's on the syllabus, but I'll be in there at the usual times. I'm just going to be on Zoom the whole time. All right. So I guess with that, I will say have an awesome day, and I will chat with y'all later.
Thank you, Bruce.
Thanks, Bruce.
Have a
Hope
good one, guys.